Suppose you are given the shown table and graph of the puck's position versus time on an inclined rail. Calculate the angle of the inclined rail. Calculate the initial position of the puck. And calculate the puck's initial velocity. First solve for C0, C1, and C2 in the parabola equation. We'll skip the details, since you've seen this many times before already. We find that C0 is the initial position of the puck, and is equal to 1.2. C1 is the initial velocity of the puck, and is equal to 1. And C2 is equal to minus 1.68. Which is equal to 1/2 g sine theta, where theta is the inclination angle, and g is minus 9.8. So sine theta is equal to 2 times minus 1.68 over minus 9.8. Which is equal to 0.343. So the inclination angle theta is equal to the arc sine of 0.343, which is 20 degrees. Suppose that we perform this experiment on another planet. Given the shown table and graph of the puck's position versus time on a 45-degree inclined rail. Calculate the initial position of the puck, the initial velocity of the puck, and the value of g on this planet. Solve for C0, C1, and C2 in the parabola equation, as we've done before. And we find that C0 is the initial position of the puck, and is equal to 0.9. C1 is the initial velocity of the puck, and is equal to 1.5. And C2 is equal to minus 1.28. Which is 1/2 g sine theta. So g is therefore equal to 2 times C2 over sine theta. Which is 2 times minus 1.28, over sine 45 degrees. Which is equal to minus 3.62. This is a factor of 0.37 times Earth's gravity, which is the gravity on planet Mars. We are given the following information. The initial position of the puck is at 1.2 meters. The initial velocity of the puck is 1 meter per second. Gravity is assumed to be the Earth's gravity, which is equal to minus 9.8 meters per second squared. And the inclination angle that the rail makes with the horizontal is 9 degrees. Calculate the time for the puck to reach the bottom of the rail, assuming the bottom is at x equals 0. And calculate the maximum height that the puck ever reaches. We are given the following information. The initial position, x0 is 1.2. The initial velocity, v0 is 1. G is minus 9.8. And the inclination angle theta is 9 degrees. We know that the equations of motion is x of t is equal to x0, plus v0 times t, plus 1/2 g sine theta t squared. Or c0 plus c1t, plus c2t squared. Where c0 is x0, which is 1.2. c1 is v0, which is 1. And c2 is equal to 1/2 of g sine theta. Which is 1/2 of minus 9.8 times sine of 9 degrees. Which is equal to minus 0.767. Now let's calculate the time it takes for the puck to reach the bottom of the rail. When the puck reaches the bottom of the rail, x of t is equal to 0. And so setting equation 2 to 0, we have c0 plus c1t plus c2t squared, is equal to 0. Since this is a quadratic equation, we can find the two solutions, using the quadratic formula. T is equal to minus c1, plus or minus the square root, of c1 squared minus 4c2 c0, over 2c2. Substituting the values of c0, c1, and c2 into this equation, we get that t is equal to minus 1, plus or minus the square root, of 1 squared minus 4 times minus 0.767 times 1.2, over 2 times minus 0.767. Then evaluating this expression, we find that the two solutions are, t is equal to minus 0.756, and t is equal to 2.06. Of course we only want the positive solution, and so the time that it takes to reach the bottom of the rail is 2.06 seconds. And you can see this on the graph. Now let's figure out when the puck is at its maximum height. The puck is at its maximum height when its velocity is 0. And so we have v of t is equal to v0 plus g sine theta t is equal to 0. This implies that t is equal to minus v0 over g sine theta, or minus 1 over minus 9.8 times the sine of 9 degrees, which is equal to 0.65 seconds. So at 0.65 seconds, the puck is at its maximum height. To find the value of the maximum height, we just need to get the position of the puck at 0.65 seconds. Plugging 0.65 into equation 2 for t, we get that x at 0.65 seconds is equal to 1.2 plus 1 times 0.65 plus minus 0.767 times 0.65 squared, which is equal to 1.53. So the maximum height that the puck ever reaches is 1.53 meters. And you can see this on the graph. An apple falls freely from a tree and hits the ground. It has 0 initial velocity, and it reaches the ground in 3 seconds. What is the distance covered in meters during the fall? What is the apple's velocity just before it reaches the ground? Sketch the graphs of the displacement, velocity and the acceleration of the apple versus time. Consider acceleration due to gravity equal to 9.81 meters per second square. It is given that the acceleration due to gravity AY is equal to 9.81 meters per second square. First, we need to find the distance covered in meters during the fall. Here, let y be positive in the downward direction. The initial velocity VOY is equal to 0 meters per second, the time t is 3 seconds, and the acceleration due to gravity, AY, is equal to 9.81 meters per second square. The equation for the distance covered is given by y minus y0 is equal to v0y times t plus half AY times t square. Substituting the values in the above equation, we get the distance covered during the fall, equal to 44.145 meters. Next, we have to find the velocity of the apple before it touches the ground. The equation for finding the velocity is given by Vy is equal to v0y plus half AY times t. Substituting the values in the above equation, we get the apple's velocity just before it reaches the ground, equal to 14.715 meters per second square. Considering y equal to 0 at the ground, the y minus y0 versus t, vy versus t, and ay versus t graphs are as shown. A toy rocket rises vertically above the ground, with constant acceleration of 1 meters per second square. When it reaches a height of 100 meters from the ground, its battery fails, and it starts falling due to the gravity. What is the maximum height that the rocket reaches? Calculate the time from the instant the battery fails, to the instant when the rocket reaches the ground. Also sketch the y versus t, vy versus t, and ay versus t graphs for this time interval. Consider acceleration due to the gravity equal to 9.81 meters per second square. It's given that the acceleration due to the gravity AY is equal to 9.81 meters per second square. Constant acceleration equations can be applied to the rise and the fall of the rocket. Let y be positive in the upward direction. The final velocity for the rise is the initial velocity for the fall. Now let us find the maximum height that the rocket reaches. We have the total height traveled by the rocket, which is y, the final position, minus y0, the initial position, equal to 100 meters, the constant acceleration ay is equal to 1 meter per second square. And the initial velocity v0y is 0. Now the final velocity for the rise is given by the equation as shown, which gives the final velocity vy as the square root of 2 times 1 times 100. Which gives the answer as 14.14 meters per second. Next, we consider the motion of the rocket, from the battery failure position, to the maximum height it reaches. Here the initial position y0, is equal to 100 meters, the initial velocity v0y, is equal to 14.14 meters per second, and the acceleration due to gravity ay, is equal to negative 9.81 meters per second square. The final velocity vy is equal to 0 at the maximum height. Substituting these values again in the velocity equation as shown, we get the equation y, the final position, minus y0, the initial position, equal to vy square, minus vy square over 2ay. Substituting the values, we get the distance of the rocket, from the battery failure position to the maximum height it reaches, as equal to 10.19 meters. Thus the final height the rocket reaches, is the sum of 10.19 and 100 meters. Which is equal to 110.19 meters. To find the time from the instant the battery fails, to the instant when the rocket reaches the ground, we consider the motion from the instant the battery fails, to the instant just before the rocket reaches the ground. Here the total distance traveled by the rocket, which is y, the final position, minus y0, the initial position, equal to negative 100 meters, the acceleration due to gravity ay, is equal to negative 9.81 meter per second square. And the initial velocity v0y is 14.14 meters per second. Now the final velocity for the fall is given by the equation as shown. By substituting the values in the equation, the final velocity vy is found. And it is equal to negative 46.50 meters per second. Next, to find the time during this fall, we use the equation, vy, equal to v0y plus ay, times t. Which gives t equal to vy minus v0y, over ay. We substitute the values in the above equation, and get the time equal to 6.18 seconds. Next, we need to find the time the rocket rises, to the time of the battery failure. Here the total distance traveled by the rocket, which is y, the final position, minus y0, the initial position, equal to 100 meters, the constant acceleration ay is equal to 1 meter per second square. And the initial velocity v0y is 0 meters per second. To find the unknown time t during the rise, we use the equation as shown, which gives time t equal to square root of 2 times y minus y0 over ay. And we get the answer as 14.14 seconds. So the total time taken by the rocket to reach the ground will be 20.32 seconds, after it first raises from the ground. The following are the y versus t, vy versus t, and ay versus t graphs, for the given time interval.